recap what we did on Saturday. So we started with an ODE, let's say, that could be nonlinear, z dot is h of z. We assumed everything is, h is good enough, smooth enough, so that we have existence and uniqueness of solutions. And so this was our ODE picture. Then we showed that there is a link to a PDE picture of, let's say we have an observable, and we then had the following Cauchy problem here, where the link was given by the generator L, and this to go from here to here was basically just applying the chain rule. And then we had another picture, the density picture, so sometimes I write ddt, sometimes I write dt, which was the adjoint operator here, the L2 adjoint. So L star rho would be minus div h rho. And we had an initial condition of z here. So these were three different pictures that we used to describe dynamical systems. So nonlinear system here, finite dimensional, infinite dimensional, but linear PDEs here. And we will use those later on if you want to do perturbation theory, because it's much easier to do perturbation theory in the linear, which we have linear operators. Then we introduced some notions of invariant measures, invariant sets, and in the end, so an invariant measure is a measure where it doesn't evolve in time anymore. So in this picture here, this would be L star rho equal to 0. And then we finished with the definition of ergodicity. So we finished the definition with is called ergodic if every invariant set let's call it A, of the dynamical system is such that either it has full measure, so full measure I just say it's equal to 1, we normalized with the measure of the whole set, or of zero measure. And we said, okay, this definition obviously depends on what we choose as our measure mu, and we discussed some examples there. So I want to, some of you asked me after, well, what does it actually mean? Like, why do we have this distinction? So I want to spend some time on the definition of ergodicity, because it's also very crucial to our endeavor then of finding model reduction. So let's just make up graphically some system here. Okay, so this is some phase space. And now let's say we start with an initial condition, z naught. So remember here, this z, these are initial conditions here. These are not trajectories. These are trajectories, this z here, we're talking about trajectories here and here. Think of them as initial conditions. They're independent variables here. But now let's just say we have an initial condition, z naught, okay, and we follow the trajectory in time. Let's say we are allowed to cross, so this is a projection, so we're not violating uniqueness, because otherwise I'm going to have trouble drawing things. So I'm crossing here. We still have uniqueness. This is just a projection. And let's say this trajectory moves around here and fills all this space here and gets arbitrarily close to some part. Let's say in here, it could take a long, long time before it eventually comes in, but it remains here, and it fills out everything. Okay, so we just follow the trajectory. So now, let's say it is such that we can draw a line. Let me draw the line here. That it never reaches this part outside here. So now we found an invariant set. It's this set here. Let's call it A1. Okay, it's invariant. I remain in there, so my dynamics remains in there. We have an invariant measure in here now. But the measure of A is neither the full measure, the full volume here, let's say, nor 0. So this system is not ergodic. So you could have the same scenario on the right-hand side. You could say, okay, let's just start with another Z0, twiddle, and do the same spiel. We follow it, and let's say it just goes around everywhere, and it never crosses here. Okay. So now we have two invariant sets. We have two invariant sets, A1 and A2. Neither of them have full measure. Neither of them have zero measure. So this system is not ergodic. Okay. So a system is, we call it metrically decomposable into two sets here. Well, then it's not ergodic. Okay. So what does it mean physically? Let's say you want to compute an average. Okay? And let's say you don't know this mu, you don't know this measure in phase space, so you can't take a spatial integral. Okay? What you would do as a physicist, you would follow this variable or the observable, along the trajectory, and take a temporal average. You measure it in time, you follow it, you follow it, you follow it, you take the temporal average. And then what you normally would like to have is some constant value. So here what you get, if you do that here, you will get some constant value if you start at this Z0. If you start at this Z0 twiddle, you will get another value. So you don't have one fixed expectation value, constant expectation value here. The expectation value depends on where you start. So the converse is, if you have a system where if you measure now the average through a temporal, your expectation value through some temporal average, and you get a unique constant value, then the system is ergodic. Okay? Similarly, in the density picture, here we have two invariant measures, right? Two ergodic measures. We have the measure defined on A1, and we have the measure defined on A2, with support just on A2. So if the system were ergodic, we would have a unique invariant measure. Okay? So it's very important. This picture I find very, very helpful in understanding what ergodicity is. So let's look formally at ergodicity and say the following statements are equivalent. So let's collect this, what we just discussed, and make it formal. So the first one is the ODE z dot h of z is ergodic. Okay. The second one is we said we want one unique invariant measure. So that means L star rho equal to 0, invariant measure. It doesn't change in time, but there's only one. So that means this equation has only one solution, has a unique solution. And I can use that solution to calculate all my averages. Everything I want, okay? Has a unique solution, and let's call it rho infinity. Okay. Now, maybe I'll start with this, Then we said here we start with our, with observable following the trajectory. And so we're in this picture here. And in this non-ergodic case, we can get, depending on the Z0, where we start, we can get different solutions. So ergodic means that constants are the only solutions of LV equal to 0. Okay. So LV equal to 0 has only constants as solutions. So that means there's no solution V that depends on Z. So that means depending on Z means depending on your initial condition, you can get different expectation values or different averages. Okay? Another way, so let's call this 3a and this 3b, is that e to the LTV, so this, remember we call this the Koopman operator, that's a propagator for these expectation values. This one, sorry, e to the LTV is our Koopman, so e to the LTV describes the evolution of the expectation value. So if LV equal to 0 is the only a solution of this, then it means that e to the LT has a simple eigenvalue 1. Okay, you bang in a constant, you get the same constant. Okay, we don't change that expectation value anymore. And this is the only solution, the constants. And point number 4 is now formalizing the idea of these spatial averages versus temporal averages. So this brings us to, this should get a bit more space, to Birkhoff's Gothic Theorem. So we know, or you can show, that if you take an observable phi, you follow it in time, okay, and now you average. And you average very long. Okay, you average, take a very long trajectory and average, so we let t go to infinity. Then this limit exists. Okay, we can show that. But this limit, what do I call this? I call it phi star. So this is my limit. It exists, but it depends on the initial condition. Okay? So if the system is ergodic, so I should say that this exists for mu almost every z naught, but it depends, but may depend on the initial condition. So now if the system is ergodic, this does not depend on the initial condition anymore, right? So no matter where you start, you explore the whole phase space. Everything you're interested in will be explored, and the limit exists and is now independent of Z naught. And that limit, this is Birkhoff's ergodic theorem, this temporal limit is equal to the spatial limit, which is the integral over this unique invariant measure. Okay? So let's formalize this. So that says this phi star of Z, I'm dropping the Z naught now, is now, does not depend on Z, I just call it phi, and this is now the integral phi of Z rho infinity, well, let's call the mu dz, and this is the invariant. This is a unique invariant measure. Okay. So people all often just say the time average is equal to the spatial average. So I can integrate over z if I know the invariant measure, or I can make a time integral following a time average following my trajectory. Okay? So an ergodic system is where those two coincide. Okay? And you can take any initial condition, you can start from any point to get the same answer in calculating this average. Okay? All right. So some remarks or some on ergodicity here. If you ask as a mathematician, just take the torus. Okay, and then we have periodic boundary conditions. Then everything is fine. I mean, you can get more fancy, but I'm not going to go into that. And then you have to look at L2, yeah. Sorry? That's right. So you need to restrict to certain functions and L2 functions. Whatever. Yeah. Okay. So some remarks. First one, let's take some function w of z, and let's hit it with the Koopman operator. And this is a useful formula we're going to derive now. And let's let t go to infinity. So what's the limit if you keep on hitting your function, your observable, with e to the lt? And what we're going to show is that this is equal to the spatial average, w I called it, of that function w. Okay. So if you keep on hitting with e to the lt now, you're going to get the average of that function. Okay. So this is a little but useful calculation. So let's take, so now we're going to prove this. So let's rewrite this as limit t goes to infinity. And now we write e to the lt w of z, no, of y. And we want an of z, so we just do delta y minus z and integrate over y. Okay? It's an equivalent formulation. And now we use the adjoint here, right? We take the adjoint of this, so e to the lt, bring it on the other side, and then we get e to the l star t. So we know that this is now e to the l star t on delta y minus z dy. Okay. And now, well, our assumption here, I should have written that, was that the system is ergodic. So if it is ergodic, then there exists a unique invariant measure. That means here we can write this formally as rho of zt is e to the l star t rho naught of z. Okay. So if this has a limit, a unique limit, no matter what I put in as my initial condition, if you keep on hitting it with now this Frobenius-Perron operator, the operator that propagates densities, you will reach the invariant measure. Yes. It works for delta functions too. Yeah? So that means this object here that limit t goes to infinity e to the l star t delta y minus z is the invariant measure y rho of y. Okay? So we can now write this as the integral wy rho infinity y dy, and that's what we had here. Okay? So this is it's a useful identity, and it's also a useful calculation to understand ergodicity. You know, no matter what you put in as a density, you will end up with invariant density. Also, what this tells us is that all the other let's keep it at that. Okay, so let's now use the ergodicity assumption to make some sense of what these invariant measures are and how we can interpret them. Sort of as a physicist, how we can interpret them. So another remark. Yeah, any integrable function. Mm-hmm. It's your observable, right? It's like something that exists for ht, for hz, you can ask what's my value. Yeah? So it's a function that goes from z into r. Yeah? Okay. Yes, so what I'm saying, the measure mu, the invariant measure, I write now as rho. There's a density with respect to Lebesgue. No, you can't always do that. For example, with a delta function, you can't, right? Sorry? Oh, then, yeah, then this would be your invariant measure, dz. Okay? So that's correct always. And then if your measure is such that you have a density with respect to Lebesgue, I can write it like this. Yes. Yeah? So now we can define the measure, this mu of A, in the Birkhoff theorem that we used. So let's choose as an observable phi the indicator function on a ZA. Okay? So this means that it's 1 if Z is in A and 0 otherwise. Okay? Just a normal indicator function. Then I can use Birkhoff's ergodic theorem. So this is now my spatial average, now equal to the temporal average. So I'm going to use Birkhoff here. So this is my spatial average, mu of A, it's my integral of the indicator function over Z. So that's the measure of my set A, because I use an indicator function. So this is limit 1 over t goes to infinity of the observable dt. So that means the measure here, the invariant measure, is given now by how much time a trajectory spends in a given set. Okay. This measures how much time do you spend in the set. Does a trajectory that goes around on your phase space spends in A? Okay. Okay. So now we established some notions of ergodicity and invariant measures and so forth. I'm going to finish the discussion on these concepts with something that I guess Jean-Luc will talk much more about, but we need it as well here, and that's a definition of mixing. So let's say we have two sets A and B, and we ask, what's the intersection of B and A if I propagated in time? Okay. And I want to know the long-term limit of this, and I normalize with B. So what does it, let's get away from the set notation. So let's take a coffee cup. So you have some initial milk in your coffee cup here, and this is my A. Now you let this milk, you stir it, and you get these milk filaments. And now you take any B, and you intersect this time. So this is now phi t A. If this was my initial A, you look at how much volume milk you have in your test volume B, right? And you normalize this with B. This is like your your coffee spoon, here's your coffee spoon, and now you ask how much milk is in it, right? Compared to how much is the volume of my coffee spoon. And then mixing says that no matter how big your spoon is or where you put your spoon in, you always get the same ratio. Okay? So this should always be how much milk did you put in initially, which is mu of A, divided by the total volume. So let's call this E. That's my total volume. Okay? So that's a definition of mixing. And if you rearrange this equation, you end up with is that mu of AT intersect with B converges to some mu of A and mu of B. There's some notion of independence here. That these, I don't intersect, I just multiply the measures now. I just take my mu of A times mu of B. Okay, so there's a notion of independence. Okay, but Jean-Luc will talk much more about this, so I'll leave it to that. I hope so. Oh. Yeah, sorry. Sure you pay me back. Okay, right, so this concludes, for now, the deterministic part. I will talk more about deterministic model reduction, but sort of the general framework of what we need to establish. For the deterministic part, we stop now. Yes, please. Oh, that's the total, sorry. That's the volume of your cup, okay? Of your coffee cup. So now we need to establish some concepts from stochastic differential equations. So let's go from ODEs now to what's called stochastic differential equations. And then the aim will be establishing the same kind of picture here. So in particular, the aim will be, if we have stochastic term, what are the generators? Okay? And then we have all the then we have the frameworks with which we can attack then model reduction. So now a brief introduction into stochastic differential equations. This is a huge topic, obviously. So I'll pick out the things that are relevant to model reduction here and what we will need later on. And okay. So stochastic differential equations, what are they? Well, we take an ODE, we just write it in this funny way, dz is h dt, so this is our z dot is h of z. And now we drive it with noise. And here we drive it with Brownian motion. Okay? We're not going to go at this stage into Levy process. I mean, Brownian motion is a Levy process, but not into this compound Poisson process or these things that you learned in Michael's lectures. But we're just going to drive it, what's my notation, with Brownian increments here, w dt. So wt is Brownian motion with unit variance. Okay. So dwt mean 0 and variance 1. And we need to specify an initial condition, z0, and the h of z is often called the drift term, and the sigma of z is often called the diffusion term. Okay? Or coefficient, so to say. It's not a term. Okay, so what are examples? So we already mentioned Brownian motion. So let's say xt or x is in stochastic analysis, people always put a small subscript t here to know that this is a stochastic process, because the z now is a random variable. So we're always going to put subscript small t here, just to stay with the literature. So let's say we have an xt, and this is the velocity of some passive scalar, so let's say of pollen in water. Okay. Then you could ask, what is dx dt, so the law of motion for such a pollen, and you could say there is a viscous drag, so this would be the deterministic part, okay, so there's some viscous part, and sorry, there's no dt here. And now we kick it with something uncorrelated, so with white noise. Okay. So this is called the Rangarajan equation. And we discuss that later on in more detail. And there we use a different name. We use the name Ornstein-Uhlenbeck process. So this is first example. And you notice, so we can rewrite this as dxt is minus a xt dt plus b wt. Right? Xit is this kind of funny thing, this white noise that is the derivative of Brownian motion that doesn't exist. Right? So physicists sometimes like to write Xit, so this is a physicist equation, and we write it this way so that everything in here is defined. Okay. The second example, so here you note that this is what's called additive noise. So the diffusion coefficient does not depend on the x, does not depend on on the process. But there are other processes that you may know that have multiplicative noise. So these are noisy population models. Or if some of you are familiar with financial mathematics, it's also used in option pricing. So let's say you have some asset, and let's say that sort of has exponential growth, you hope. Right? But let's say the growth rate alpha, we know the mean, and it's sort of fluctuating. Okay? So if now alpha is some a, which is a constant, plus some noise, and again we use white noise here, so at each time gets a different value. Okay, so it's delta correlated, there's no correlations here. Then you end up with this system here, so you got a xt dt plus b xt dwt. So now you have multiplicative noise here. Okay. So these are just two examples. But we want to find solutions. How do we find solutions here? The problem is that this thing here, Xit, doesn't exist, right? This is very rough. Like Brownian motion is nowhere differentiable. Okay? So we try to formulate a solution differently, and we say, okay, the solution, let's write it as an integral, and then worry about the integral we're going to get. Okay? So this here, there's nothing that goes to infinity here at the moment, right? If you write it this way, you don't have dw over dt. Dt is, right? We multiply it through in some sense with dt. So let's just take the integral of this. So the precise interpretation of the solution of an SDE, or the solution of the SDE, and its solution is we integrate. So z of t, that's my d of z, is z naught, plus integral 0 to t h of z of s ds, plus integral 0 to t sigma of Z of S dWs. Okay? So in some sense, we transferred the problem now to integrals. So you have to think about the integrals. Well, that's given, right? Maybe it's randomly distributed or whatever, but that's fine, that's defined. What about this one here? So Z of S is now a random process. Okay? Ws is extremely, the Wiener process, very wiggly, right? In any time, kind of, it has infinite length, right? It's no way differentiable. So H will be very, very wiggly. Right? So we're integrating a very, very wiggly, rough function, but it will only be as worse as the Wiener process. Okay? So Wiener process is continuous. So this integral makes sense if you use Riemann integration. Okay? We have a continuous function, so this is a continuous function. It's very rough, but it's continuous. Okay? So this integral in some sense is fine. We can use normal Riemann integration. Well, you want to know, is it unique, for example? Okay. It's a function of t that will depend on your initial condition and will depend on a realization of this Wiener process. So this is a random function. Let's assume this is a function of time now. So this is a w of t. And it's just some given driver. And it's nice, it's smooth, let's say it's a sinusoidal. Okay? Then this is a non-autonomous ODE. So you can find solutions. It will depend on time. Right? So now the question is, well, this is still, in some sense, a non-autonomous equation. You can still treat it as something that's driven by a time signal that's given, but random now. So we don't know what it is. We only know the distribution of it. Okay? So if you put it in a computer, so finding a solution, that's a good question. So this is time, and let's say this is our Z of time, Zt. This is a random process. So you put it on a computer, that means if you put it on a computer, you draw random numbers here. Okay? So you start at some Z0, and now dzt, if you make it really small, okay, so this would be your Z of t equal to Z of naught, and then so forth. You do delta t, you evaluate it, let's say, at the left point, at the Z of naught, this at Z of naught, and now you draw a random increment, which is normally distributed, so you look at a random generator. Okay? So you're going to get some pass here, let's say, right? So now you give the same program to one of your friends, right? They have a different computer, they have a different compiler, so the random numbers that they draw will be different. They all start at Z0, because, I mean, that's how you programmed it. But now you're going to get a different initial, seed for your pseudo-random generator. So you're going to get a different trajectory. Okay? But there will be certain properties. For example, if this is an ergodic process, we'll see there will be a density. Okay? So at each t, all those different realizations that all of you get here, all these different trajectories, if you make a histogram, they will give me that PDF, or that density that is associated with the density that we get from this process. Does that answer your question? Yes. That's right. That's right. Given, and if you really want to draw a solution, you have to specify your random driver. Okay? But it's a random driver, so someone else might specify another random driver. But of course, it has to obey. The constraint that it's normally distributed with mean 0 and variance 1. Okay? Now that's an important point. Like, what does it mean, the solution, right? So this is now dependent on the realization of the Wiener process that you draw. No, the DWs. DT, sorry, yes. sorry. Crazy. That's right. Yes. Okay. So now we understand what is a solution. It depends on what we draw here. Okay? So we're drawing something that's very rough, Wiener process. Okay. So this thing here has infinite, like the DWs, right? They can get very large. So we have something very rough in here, and this has it's not a bounded, doesn't have bounded variation anymore. So the total variation of this, which means that like the length, is infinite now, or can be. Yeah, it's infinite. It's not bounded. Okay, because you're so wiggly that the length of your Wiener process is infinitely long. So this integral here is a problem. Okay? So let's just say, I don't care. I define it this way. I just write down here, okay, well, this is just dws, ds, and then I use my normal Riemann integral, right? Then I have my ds, that's fine. But here we have a problem, dws, ds, right? Remember dws, ds, this scales like square root of ds, that was the dt that I missed there, right? The variant, over ds. So this is 1 over square root of ds, so I can't really let ds going to 0. Okay? So this is not possible. Our first guess doesn't work. Okay? Well, then we could say, okay, let's define an integral. And so this is my s. And we take smaller and smaller partitions here, equidistant in little ds of my time. And we say, okay, this is now the sum over all those k. So we take, let's introduce a capital K, so that such that k ds is some t. And so these individual tks here, they are just k times ds. Okay? So now we evaluate this dws as the ws plus 1 minus k plus 1 minus wk, and so forth. Okay, so we just discretize the time and try to evaluate this integral. So we would get our w of tk minus w of tk minus 1. That's our ds. And let me call this one here for now an f of s, because it's easier to write. Okay? It's just a function, any function, f of s. So I need to now evaluate this function here somewhere in this interval. Okay? So I call this tau k, and tau k is smaller than tk and bigger or equal to tk minus 1. So the tau k is somewhere in between. Okay? So if you do normal Riemann integration, it doesn't really matter where you evaluate your function in there. Okay? All these limits will converge to the same answer. And let me just write here. So this is now k goes to k, I guess from 1 here, and we let k go to infinity. Okay, so we take finer and finer partitions, so our delta s here will be smaller and smaller. Okay, yep. Well, we need to find a solution here. We need to define what is a solution. You are interested maybe only in the average. Other people might be interested in the actual trajectory, yeah, in the actual solution. Okay. But even the average here, I mean, you can't just even the average you could just say the DWS is 0, right? But then you have to see where's the Z defined, right? Does the Z know about the DW or not? Is it dependent on this DWS or not? Are they independent, right? So issues like this, even when you do average. So let's define this integral. Okay. So now what you find out if you do that is that the solution here, what you get out in this limit, will depend on where you actually evaluate. Okay? And that's due to this wiggliness of the Brownian motion. Okay? And there are lots of choices. Each of those choices will work. Yeah? Sorry? How can you find what? The Tokay is, at the moment, we don't know what it is. We just say there is a Tokay. Yeah, it lies, so this is tk minus 1. So we know tk minus 1. We know tk, and there are some ds, we said, apart. And now we just say, let's evaluate it somewhere in the middle. No, somewhere in between, not just in the middle. The middle is a special choice. Okay? So if you do normal integration in classical calculus, it doesn't actually matter where you put it in. Here it matters. Okay? The problem is, it's a roughness, and it's that these things here, they are like if you make it smaller and smaller, they don't sum up to something finite. Okay? Say again? Exactly. It gets worse and worse and worse, actually, because it gets longer and longer and longer, right? Sorry? No. So that's something, I'm not going to go through all these calculations. So if you look at this limit here, then this will depend on where you're going to evaluate. Okay? So you can make a choice, say, okay, I define my integral, so whatever the solution is understood as this integral where I evaluate at some specified Tokay. That's what you have to do. So when you talk about a solution to this SDE, you have to say how you interpret this integral. Okay, you can't just say, well, that's a solution here. You have to say, how do I interpret this integral? That means, where do I actually evaluate this? Okay? No. Oh, well, this is f of, this is of Tokay, but here this would be sigma of z of Tokay. So you say you know your solution up to here. Let's write up. That's correct. Up to here. Oh, did I make? I can still define it. This is not defined. But this is an implicit equation for my z. This doesn't really define my z of t4, right? It's an implicit equation. The z comes in here. So I keep it implicit. This is not numerical integration scheme here. Yeah? Well, it's not the numerical scheme at the moment because of that issue, right? It's still an implicit. It's just a definition of the solution. Yes. So let me present the two main cases that people use, okay? So where they evaluate. So the first one is called the Ito stochastic integral. So in the Ito case, you say you evaluate at the most left point. So in the Ito case, you say I of t is now my limit, k goes to infinity, of f of tk minus 1 times wtk minus wtk minus 1. Okay. No. You mean whether this is less random? This is always random. Oh, that just means the variance, but it's still a random. That means how far can you deviate in one time step? Okay. Do you know there's this? Do you know the drunkard picture for Brownian motion? Yeah. So the random walk with the same probability. So the longer you wait, like if you not do one step, you can't go too far away, right? But if you wait long enough, I've made lots of steps. I move that way. So that's what this means here. So the variance, which is the uncertainty of where is a drunkard, depends on time. So you lose, you can't localize a drunkard for longer times anymore, right? You know the mean is 0. So if you take lots of drunkards, and you now take the average, you'll be at 0. But does it make sense? In one time step, I can't go very far away. Just one step. Okay? But if you integrate for long, but it's still random, right? I don't know whether I'm left or right. Okay? Even for the first step. Okay? So, this is the Ito definition. The Ito definition has some kind of nice property. The nice property of the Ito definition is, you see, this is my dw, tk minus tk minus 1. This is f of tk minus 1, and now your comment comes in. This only knows about the noise that happened before, right? Everything up to tk minus 1 it knows. And this is the next increment. So that is independent of that. So if you now take the expectation value over, so this is average over the driving Brownian motion path. So if I take the expectation value of this Ito integral, then this is 0. Because we have an independence here of this stochastic random process and this random variable and this one. Okay? So that's where your argument comes in. Okay, where is it? Where's the tk? This one only knows about the noise that has already passed, the increments that are already passed. This is the next increment. So financial mathematicians and mathematicians in general like this because, this is a fair game. This only depends on t, so it doesn't change. The expectation value is always 0. So it's like a fair game approximation that mathematicians call a martingale property. But you pay for this. And where did I write this? You pay for this. So if you actually calculate something like ws dws from 0 to t, or from t0 to t1. Well, let's do classical calculus. Classical calculus would tell me, well, this is 1/2 w squared evaluated at t1 and minus evaluated at t0, right? Okay. But if you use this definition here, what you find out, you can do that. It's a bit fiddly, but you can actually do that using this definition here. What you find out, that you have to subtract here a term minus 1/2 t1 minus T naught. Okay. So you have this nice mathematical property, but what breaks down completely is classical calculus. So classical calculus doesn't work. Okay. So the other often used choice is what's called the Strattonovitch integral, and that integral is such that classical calculus does work, but you don't have that property here anymore. And you run into problems of that you evaluate now somewhere in the middle where you don't know the noise. Okay? So, okay. So the other one is called the Strattonovitch integral, and that's where you are evaluating at the half point. And the way we write the half point is an average over the two endpoints. So this is my average over the two endpoints. So effectively, we are evaluating at the in the middle, and then we have times W tk minus W tk minus 1. Okay. So if you use that, then classical calculus will work. And if we now take WS dWS with this interpretation, then indeed we have classical calculus. Okay? So you can get from one interpretation to the other one. Sorry? How I got to here? I didn't do that. We don't have the time. I can show you, but I don't want to do that in the lecture. So if people are interested in how to do that, we can do that. It's only using this definition. Okay? But I only want to stick here to what we need later on. So we don't need to show these things. We just need to be aware of the difference. And you can get from one form to the other one. There are formulas to do that. Okay. So I have only 1 minute remaining. I don't want to. I just integrated ones, yeah. It's just a different expression of the solution. This one here, that's right. This depends. Yes. But the solution depends on how I have to specify what type of noise do I use. Do I use a noise where evaluate in the middle, or where evaluate to the left or to the right? Okay. No. You have to specify, that's right, you have to specify that before, exactly. So whenever we write down an SDE in this form here, we have to say in what sense do we interpret this noise? Are we talking about an Ito, in the Ito sense, or in the Strattonovitch sense, or in any other sense? We have to specify that. And once we specified it, you can show existence and uniqueness, okay, and everything is fine. I'm not going to go into that, but it's again the same thing. This is, Lipschitz, and if this is Lipschitz, you have existence and uniqueness of the solution. But you have to specify what you mean by that noise, how you interpret it. Okay? And uniqueness, by the way, is, of course, because these are random processes, it's just the probability of one solution being equal to another solution is 1. Okay? Or of a different one is 0. Yeah. That's correct. So that means you always have to say that this equation only makes sense if you specify how you interpret it. Okay? But now the question is, well, hold on, I got a physical system, what do I use? Right? And there, well, I can comment on this now, but I want to discuss this in more detail a bit later. So if you have something that's fair, right, like in financial mathematics, you want to use this interpretation. Okay? But if you have something, and that's what we're going to discuss in more detail, that's our aim. Our aim later on will be we want to have a deterministic chaotic system, multi-scale system, where we can show somehow that the limit is an SDE. So the limit is something stochastic. We started entirely deterministic. The limit will be stochastic. So the question is, what should the noise now be? Okay? We know it's an SDE. We can derive it. We can derive this sigma. But we have to say, what is this noise? And now think about what you want. You have a dynamical system. A dynamical system, classical calculus works. Right? We can differentiate. Everything works fine. The limit now is an SDE, a noisy system. So you want that their classical calculus works if it should describe. So you get the limit is something rough, but it's the limit of something that is, it's the limit of smooth functions that are smooth dynamical systems going to something rough. So classical calculus should survive, and then you use the Strattonovitch interpretation in this case. But if you specify one solution, if you just specify one interpretation, let's say you say, okay, this is Ito, right? You can express it into Strattonovitch. You'll just end, we're going to show this. You'll just enter the, change the drift term. Okay? So you can seamlessly move from one to another one. But you have a different drift term, so you have a different solution. Okay? So you can move from one interpretation to another one, but you change the solution. It's kind of weird, right? You say, come on, I have it written down here. Surely there must be a solution. But no. You have to specify where you evaluate. Yes. Well, as I said, if you're looking at financial maths stuff, you use the Ito, okay? Because you have a fair game. If we use, if you look at this diffusive limit of deterministic dynamical systems, the limit will be Strattonovitch, because we want the classical calculus to survive. Okay? But you could, you still. This is when you say here about averaging or something, you're only interested in averages. You can specify later on by you just say, okay, I'm going to interpret it by Ito, but then you play around with these parameters here to get the statistical behavior that you want. So to go from Strattonovitch to Ito, they're very different, right? But I can go from one interpretation to the other one by changing the drift term. So you can play with those. If you just want to do modeling, if that's your question, if you just want to do modeling, you can just say, okay, I'm using Ito, that's it. But now I play around with these coefficients to get the behavior I want. If you want to do fitting, or if you want to fit to something, right? Sorry? For large number equation, yeah, people use Ito normally. That's right. Where did I write down? You mean what you use here? You can specify whatever you like actually in here, right? The SDE, whether you, let's first do maybe we should refer all these questions for after we actually said what do we mean by changing the calculus and how do we get from one interpretation to the other one. Okay. But you can take any interpretation you want. If you just want to do modeling, here you just want to do some modeling, right? So you just want to get the behavior out, so you can just say, okay, this is Ito, and then you just fit your parameters A and B to fit your model. Okay? But you have to make a decision. You have to tell the other people, when I talk about these solutions, I'm assuming here the Ito formulation. Okay? So that other people can interpret your result. Okay.